Hello everyone, hello Jean. Today
Hello.
it's the third video of our 6-part interview with Jean Bricmont on the foundations of quantum mechanics. So if you haven't seen the first two videos, you should. Especially you should watch the second video in order to really understand the video of today. And so if you don't know Jean Bricmont is Professor Emeritus of Theoretical Physics at Louvain University in Belgium. And he has written many articles on the subject, on the topic of the foundations of quantum mechanics. And he has written a very technical book on the subject, which is Making Sense of Quantum Mechanics. And I will put the link of this book in the description of the video. And he has also written a popularized version of this book. The title is Quantum Sense and Nonsense. And today, so in the previous video, we talk about the Bell theorem, and Jean explained to us why Bell theorem is a proof for non-locality in quantum mechanics. And today, Jean will talk about the misunderstandings of Bell theorem, because these misunderstandings, are widespread in the physics community. So I let Jean talk.
Okay, thank you. Thank you very much, Arnaud. Okay, I will... Okay, so we will discuss some of the misunderstanding of EPR and Bell by, I must say, famous physicists. But these misunderstandings are very widespread in scientific and popular literature. And so we'll start with the misunderstanding of Einstein, Polotski, Rosen, and then turn to those of Bell. I think this video is pedagogical in the sense that it shows you how you can misunderstand what I've been trying to explain in the previous one on Bell and non-locality. The most common error concerning the article of EPR consists in thinking that the aim was to show that one could measure, for example, the spin in one direction on Alice's side and in another direction on Bob's side for the particle with this state. And of course, if you measure it on one side, since they are perfectly correlated, you know it on the other side. So if you measure one in one direction on one side, another direction in another side, you would know the spin in both directions simultaneously, and the spin along two different directions cannot be measured simultaneously according to ordinary quantum mechanics. So this means that the people think that the goal of EPR was to refute this limitation on our ability to make measurements. But it was quite explicitly not the goal of EPR. What they wanted to do is to measure quantities that are impossible to measure simultaneously according to quantum mechanics. They did not want to do that. They wanted to show that if you can learn something on a physical system by making a measurement on a remote system, then unless there are actions at a distance, which they did not even consider, this thing must already be present before the measurement can be made on the remote system. This something that you can learn must pre-exist to the measurement on the remote system. If you want to be generous, you may consider this misunderstanding as being Bohr's response to EPR, because so EPR came with their article and Bohr made a response, which I think is very ununderstandable. But anyway, I say it's generous because Bohr's answer is very unclear. His answer is at the level of epistemology. Is what can we know? Can we know the value of spin on both sides, for example, on different direction? While EPR's argument was about ontology, namely about what exists. And Einstein explicitly denied, unfortunately only in a letter to Schrödinger, that he wanted to simultaneously measure quantities that cannot be measured according to quantum mechanics. He didn't care about what you can measure or not. Nevertheless, Bohr's answer is probably what physicists who think that Bohr has refuted EPR have in mind. So I think that's a misunderstanding of EPR and, of course, of the idea that Bohr was right and Einstein was wrong.
So, okay, so to emphasize your point, the misunderstanding is that according to some physicists, the EPR paper had the goal to show that we can measure the spin of one particle, sorry, in two different directions, instead of showing that if you take a pair of particles which are intricated, either you have hidden variables or you have non-local actions or actions at distance.
Yes, but of course, the argument of Einstein, I mean, the misunderstanding of Einstein would be that they would measure the spin in different direction, but of course on the two different particles. It's also in his entangled state. Okay, you would use the entangled state to measure it in one direction on one side and the other direction on the other side, and then you would know it in both directions because they are perfectly correlated. In fact, if locality was true, it would be possible. But according to ordinary quantum mechanics, of course, when you do a measurement on one side, you collapse the wave function, and then, of course, the measurement on the other side is not the one you would have if you measured the other side first. But of course, the people who speak about ordinary quantum physicists usually don't understand the consequences of this non-local collapse. Anyway, I want to, Einstein, there's a book called Einstein, Philosopher Scientist, where everybody has been who was alive at that time has been writing about Einstein, and Einstein responded to the critique in this book. And he stated his position in the form of a dilemma. He said the paradox, or the perfect correlation, forces us to relinquish one of the two following assertions. The description by means of the wave function is complete, or the real state of spatially separated objects are independent of each other. So in our language, either we have hidden variable, the wave function description is not complete, that's the first possibility, or there exist actions at a distance, that's the second possibility, namely states of spatially separated objects are not independent of each other. He was also very clear in his exchange with Born in 1948. He said if one asks what, irrespective of quantum mechanics, is characterized of the world of ideas in physics, one is first of all struck by the following. The concept of physics relate to a real outside world. That is, ideas are established relating to things such as bodies, fields, etc., which claim a real existence that is independent of the perceived subject, of the perceiving subject. So, of course, Einstein takes a realist attitude with respect to science. It is further characteristic of these physical objects that they are thought of as arranged in a space-time continuum. The essential aspect of this arrangement of things in physics is that they lay claim at a certain time to an existence independent of one another, provided these objects are situated in different parts of space. And then he's very explicit. He said the following ideas characterize the relative independence of objects far apart in space, A and B. External influence on A has no direct influence on B. So that could be a clearer way to say there are no actions at a distance. And it's interesting to see how Born reacted to that. So there was an article, that's what I just quoted, is part of an article that Einstein sent to Bohr, and he said, read it as if you came from planet Mars or something like that. You know nothing about these ideas, and yet Born completely misunderstood it, because he said the root of the difference between Einstein and me was the axiom that events which happen in different places A and B are independent, in the sense that an observation on the state of affairs at B could not teach us anything about the state of affairs at A, which is of course completely silly. In the previous talk, I gave the example, you take a picture, you cut it in two, you put them each part in envelopes, and one mail to Tokyo, another to New York. And if people are aware of what's going on, if you open the letter in Tokyo, then you know that the person in New York has the other half of the picture, or vice versa. Okay, so of course, state of affairs at B can teach us something about the state of affairs at A, but it cannot influence the state of affairs. You see, that's very remarkable.
Yes,
And
this is in fact, this is the starting point of the EPR argument.
Yeah, of course.
Yes.
Well, it's the starting point of EPR argument that you could, I mean, the assumption that EPR do is that external influence on A has no direct influence on B. And now if things are correlated, how do you explain for them?
Yes, it's locality. Yes, that's the locality assumption and the perfect correlations.
Well, no, you assume locality and then you say, how do you account for the perfect correlations? And the way to the only way I see to account for them is to say that the results are predetermined. So Bell says misunderstanding could hardly be more complete. Einstein, of course, had no difficulty accepting that affairs in different places could be correlated. As the example of the picture, the two halves of the picture. I mean, there are correlations between things at different places all the time. But what he could not accept was that an intervention at one place could influence immediately affairs at the other. And then he had these references to Born are not meant to diminish one of the towering figures of modern physics. They are meant to illustrate the difficulty of putting aside preconception and listening to what is actually being said. They are meant to encourage you, dear listener, to listen a bit harder. Of course, once you have a misunderstood EPR, it's easy to misunderstand Bell, because the main source of the misunderstanding of Bell stems from the idea that Bell simply demonstrated that hidden variable could not be introduced to complete the quantum description. Of course, that forgets EPR's argument that the assumption of locality implies the existence of such variables, and therefore that Bell demonstrates the existence of non-locality action or actions at a distance in nature, indirectly.
Because we can summarize that by saying that that Bell theorem is a two steps argument, and the first step.
The second step is the second step in a two-step argument.
Yes, but I mean, yes, okay. I meant if you take the whole reasoning, so you have first.
Yes, if you take EPR and Bell, it's a two-step argument.
Yes. So and the EPR argument starts yes from locality and goes to hidden variables, and then if you start from the EPR argument, you can derive, as Bell did, statistical constraints.
Yeah. Yes, that show that you cannot introduce those variables. And in fact, I will repeat what he said, but Bell was very clear. And I will repeat it to show, I will already said it last time. You see, he summarized the logic that led to the impasse being non-locality. EPR puts B because actually the way it's formulated with spin and so on is due to Bohm and not to EPR. The correlation, the fact that you have this perfect correlation are such that the result on one side immediately foretells that on the other whenever you ask the same question or whether you measure the spin in the same directions. If we do not accept the intervention on one side as a causal influence on the other, so if we do not accept action at a distance, we seem obliged to admit that the result on both sides are determined in advance anyway, independently of the intervention on the other side by signals from the source and by the local magnet setting. But this has implication for non-parallel settings. When you do the measurements in different directions, we conflict with those of quantum mechanics. So we cannot dismiss intervention on one side as a causal influence on the other. So we cannot dismiss actions at a distance in nature. Should be emphasized that in this argument or in any of his argument, Bell does not assume determinism. He assumes, of course, this perfect correlation, but these are empirical facts, sometimes called determinism, but that's nothing to do with whether the whole theory is deterministic or not. He doesn't assume realism. He doesn't assume, he derives, if you wish, the reality of this hidden variable from the assumption of locality and the perfect correlation. He does not assume hidden variable. He derives hidden variable like EPR did. Okay, so these, everybody says, oh, Bell has some hidden assumption. No, there is no hidden assumption of that sort. And he also complained about the misunderstanding. He said, my own first paper on this subject starts from a summary of EPR argument from locality to deterministic hidden variables, if you wish. But the commentators have almost universally reported that it begins with deterministic hidden variable. And of course, what is called deterministic hidden variable is the value of the spin pre-existing to any measurement and whose existence was deduced by EPR from the assumption of locality. And now I'm going to quote several famous commentators who missed the point of Bell. So maybe you should be, the listener should be encouraged to listen a little harder to see, but not to make those mistakes. So Gell-Mann, who is a genius and the discoverer of the quark and the winners of the Physics Nobel Prize in '69, say some theoretical work by John Bell revealed that the EPRB experimental setup could be used to distinguish quantum mechanics from hypothetical hidden variable theories. After the publication of Bell's work, various teams of experimental physicists carried out the EPRB experiment. The result was eagerly awaited, although virtually all physicists were betting on the corrections of quantum mechanics, which was in fact vindicated by the outcome. And so, of course, he says that, so Bell sees this as a conflict between hidden variable and quantum mechanics wins, but he doesn't realize the implication for non-locality. And in fact, Bell was showing the example of Bertman-Sachs. I think this Mr. Bertman was working at CERN, and he was actually a physicist, I think. And he had the peculiarity of wearing socks of different colors all the time. So if you see a sock which is pink, you know that the other one is not pink. But of course, Bell takes an example, as in the discussion with Born, of correlation. But of course, the color of the socks pre-exists to our observation of them. So you just learn something about the other sock by doing at one sock. And the whole point of Bell's article, the Bertman-Sachs, it's called Bertman-Sachs and the Nature of Reality, is to say that this is not what happens in quantum mechanics. In quantum mechanics, you sort of create the color of the socks, or at least you create the values of the spin because they don't pre-exist to your observation. But Gell-Mann's reaction, again, is missing the point. He says the situation like that of Bertman-Sachs. Bertman is a mathematician, actually I think he was a physicist, but who always wear one pink and one green sock. If you just look at one of his feet and spot a green sock, you know immediately that his other foot sports a pink sock. Yet no signal is propagated from one foot to the other. Likewise, no signal passes from one photon to the other in the experiment that confirms quantum mechanics. No action at a distance takes place. So he misses the point entirely of Bell's article. And in fact, he met Bell, he listened to him. Eugene Wigner was another Nobel Prize in physics, also considered Bell's results as an argument. He said, in my opinion, the most convincing arguments against the theory of hidden variable was presented by John Bell. Another famous commentator is Stephen Hawking, who is one of the, he's dead now, but his books were very famous, mostly on cosmology. But he says Einstein's view was what would now be called hidden variable theory. Hidden variable theories might seem to be the most obvious way to incorporate the uncertainty principle into physics. They form the basis of the mental picture of the universe held by many scientists and almost all philosophers of science. But these hidden variable theories are wrong. The British physicist John Bell, who died recently, devised an experimental test that would distinguish hidden variable theories. When the experiments were carried out, the results were inconsistent with hidden variables, which is of course true, but it misses the main point, which is the non-locality. And there are two, for example, a professor at MIT and one of Princeton. They say, could the apparent quantum randomness be replaced by some kind of unknown quantity carried out inside particles, so-called hidden variables? CERN theorist John Bell showed that in this case, quantities that could be measured in certain difficult experiments would inevitably disagree with quantum predictions. After many years, the technology allowed researchers to conduct these experiments, eliminate hidden variables as a possibility. Again, it misses the point. And even, I must say that even in the 2022 Nobel Prize Committee, he makes that mistakes in that sense. He speaks of John Clauser, who was the first to do these experiments. He developed John Bell's ideas leading to a practical experiment. When he took the measurement, they supported quantum mechanics by clearly violating a Bell inequality. It means that quantum mechanics cannot be replaced by a theory that uses hidden variable. In the next talk, we are going to show exactly that it can be replaced by, not replaced, but completed by a theory that uses hidden variable, but of course not the hidden variable that Bell has proven cannot exist. Not those hidden, some other hidden variable, but the statement here is too general. And I could go on and on with these quotes. I have more of them in my book, but I like the way David Mermin, who is he's a physicist at Cornell, and sometimes he says strange things, but here it's pretty funny. He says contemporary physicists come in two varieties. Type 1 physicists are bothered by EPR and Bell's theorem. That's of course me, that's us. Type 2 are not, but one has to distinguish two subvarieties. Type 2A physicists explain why they are not bothered. Their explanation tend either to miss the point entirely, like the response of Born to Einstein, or to contain physical assertion that can be shown to be false. Type 2B are not bothered and refuse to explain why. Their position is unassailable. And there is a variant of type 2B who say that both straighten out the whole business, but refuse to explain how. It's pretty ironical, but I think it's pretty correct. And he mentions an anonymous Princeton physicist who told him anybody who is not bothered by Bell's theorem has to have rocks in his head. Now, of course, okay, it's a survey of the misunderstanding. I think the misunderstanding is enormous, and I hope to have demonstrated it. But there is a common objection, which is not a real objection, but a real question, which is not just due to misunderstanding, and I want to spend the last few minutes of this talk on that. People say, isn't non-locality contradicted by the theory of relativity, which implies, what is loosely say, people say nothing goes faster than the speed of light in a vacuum. That's usually what people remember from relativity. Well, there the answer is complicated. First of all, you need to be clear about what the theory of relativity implies. It certainly implies that you cannot transfer matter faster than the speed of light. You cannot transfer energy faster than the speed of light. You cannot transfer messages faster than the speed of light. So I cannot communicate with you faster than the speed of light. But the EPR-Bell experiments do not violate any of these principles. That would require some work, but they don't really, imply any of these violations. You cannot transfer matter, energy, or messages. But you can transfer information. That's a little bit strange. Why isn't information a message? Well, suppose I send you a message in Chinese. That's a message, and you don't know Chinese, and you don't it's information, but it's not a message. In order for it to be a message, you need to translate it, and of course now you can use automatic translation, okay? But you need something else. Yet the message in Chinese is not a message for you, but nevertheless it has information, of course. So for example, in the Alice and Bob experiment, you get information about the result of the spin measurement on the other side if they are done in both directions, in the same direction on both sides. So there is a certain information transfer, but not messages. And if you really analyze relativity, relativity does not prevent you from having this instantaneous transfer of information. And in fact, this is at the basis of quantum cryptography and quantum teleportation, but this is too complicated to explain in this video. But of course, if you speak of EPR-Bell, the fact that there is some transfer of something between the two parts, certainly it goes against the spirit of relativity, because the spirit of relativity, as understood by Einstein and many others, was in fact local. Einstein certainly believed the world was local. He didn't consider non-locality as a possibility for a second, and he certainly thought that, so his notion of relativity was linked to locality. Now you have to think about relativity and combine it with non-locality, and that's not easy. There is no easy way out. But relativity is a well-established theory, and non-locality is well-established too. So you can't just say, I'm going to get rid of one of them. You have to live with both. And I'm saying you can live with both, because there would be a straight contradiction if you could transfer matter, energy, or messages. You cannot. With this EPR-Bell, you cannot. But you can transfer some sort of information, and that, I must say, it's a little bit strange from the point of view of relativity. Anyway, I will stop here because I want to go. I will just want to give the gist of the argument and not go into too many details.
Okay, maybe we should add that Bell was one of the greatest champion of a hidden variable theory, because we saw
Bell,
a lot of quotes saying that Bell proved that hidden variable theories have been refuted.
Yeah, the professor in my university who made a sort of a book review of Bell's book, and he said there are two Bells, one proving that no hidden variable cannot exist, and one trying to find a hidden variable theory. But of course, Bell was perfectly consistent, because Bell was very much interested in the de Broglie-Bohm theory, which, or Bohm at least, Bohm's paper, 1952, which we'll discuss in the next video.
Yes.
And he was but he knew that this theory was non-local, so he was wondering whether the non-locality was an unavoidable consequence of quantum mechanics, or whether one could maybe get rid of it.
Yes.
And that's exactly what led him to his inequalities and the discovery that you cannot get rid of it. But of course, he was always, in all his book, he was proponent of hidden variable, and he did not refute the possibility of introducing hidden variable. He refuted the possibility of introducing those particular hidden variable, namely the spin values, that were necessary in order to save a local view of the world, as shown by EPR. So I don't want to repeat myself too often, because it gets to be boring, but you have to get together the two-step EPR and Bell.
Yes, yes, because the root of all these misunderstandings is the fact that people, I don't know, don't understand, or I don't know if it's if that's the problem. But there is the EPR argument before the Bell theorem, and you have to combine both in order to prove non-locality. Okay.
Yes. Okay. So
thank you, Jean.
So thank you very much, Arnaud. So we stop now?
Yes.
Okay.